Welcome to Podcast 3-4 Polygons, Part 2. In this lesson, we're going to look at the patterns of the angles of polygons, and that is on all polygons, and then specifically regular polygons. And then we're going to look at a procedure for how to determine the angle measures of regular polygons. First, a little bit of vocabulary. It's important that we understand the difference between an interior and an exterior angle of a polygon. So here's just a polygon, or a portion that you can see. The interior angle is going to be at any one corner. You have an angle formed at any one corner. So we have many interior angles. But also at that corner we could extend an edge and create an angle that's outside the polygon. Here's a particular angle, so if I extend every edge, I can create exterior angles. You might say, well, why don't I extend the edge in the other direction? Well, it's certainly possible. We can go this way and create exterior angles all the way around like this. So exterior angles, interior angles. And then the question comes up, well, can I have it extend in both directions? Well, certainly you could. It's just not something we're going to do. Because at any one intersection, we only want to consider one exterior angle. This is the interior angle. Just one of these will be considered the exterior angle. This is considered just a vertical angle to the interior, or this would be a vertical angle to that exterior. But again, at any one corner, we only want one interior and one exterior. Therefore, if there are 5 sides to the polygon, there are 5 interior angles and 5 exterior angles. One thing I'd like to make a note of, that at any one corner or vertex of the polygon, our interior and exterior angles all have one thing in common. It's something we learned a long time ago. The interior and the exterior are supplementary, also known as a linear pair. The next idea is a pattern that exists with these interior angles of irregular or regular polygons. So let's take just a 3-sided polygon, a triangle. Obviously there are 3 sides, and we can clearly see that there is one triangle that exists. But what is the sum of this angle and this one and this one? Well, we know that rule. That's 180 degrees. No problem. But when we have a 4-sided shape, what's the sum of this angle plus this one plus this one plus this one? Well, that might not be as obvious. But what can be obvious is we can take this shape and break it into 2 triangles. And now we know that we have a triangle here, so with 2 triangles, 180 degrees per triangle, 180, 180, that's going to make a total of 360 degrees as a sum. Key word here is the sum of the interior angles. So let's go to 5 sides. 5 sides, how many triangles can this create? Well, I'll take one vertex and we can draw to every other vertex. And now we have created 1, 2, 3 triangles. 180 degrees per triangle. Grab your calculator, hit the buttons, and we have 540 degrees as a sum. And do you see the pattern being formed? 6 sides will break into 1, 2, 3 diagonals drawn, but 1, 2, 3, 4 triangles. Obviously, with one more side, we're creating one more triangle, and now we're up to 4 times 180, 720 degrees. So what's the actual pattern, or what's the actual rule? We have the number of triangles times the sum of that triangle gives us our answer. The number of triangles times the sum of the angles of a triangle, 180, gives us that answer. So this number times 180 gives us that. So as a rule, or as a theorem, the sum of the interior angles of any polygon is the number of sides, take away 2, and that gives you the number of triangles. Look at that again. The number of sides subtract 2 is the number of triangles. The number of sides subtract 2 is the number of triangles. And then 180 degrees per triangle. So it's the number of sides, take away 2, gives us the number of triangles times 180 per triangle. And that is our first very important theorem. Here's an example of the use of that theorem. How big is this angle here? Well, I have 5 angles. It's a pentagon. If I knew what all 5 added up to, I could determine this last number. So it's the sum of the interior angles of that pentagon, and then I can figure what's left. Pentagon being 5, take away 2, times 180 degrees. The sum of all these angles has to be 540. So if I do 90 plus 105 plus 100, how much is left over to create a grand total of 540? And you'll get an answer of 155. Then again, estimation, it also looks like 155, so that makes sense. Going back to our sketchpad picture, I wonder if there's any other kind of rule or formula that might be true about exterior angles of polygons. So here is my pentagon, and I have 5 angles. It's irregular, therefore they're all different. So, and by definition of irregular, they all can be different. There's not one rule about the size of an individual angle here, but if we were to take all of these angles and add them up, you'd find a very important fact, that the sum of these 5 angles is 360 degrees. So again, the theorem says the sum of the exterior angles of any polygon is 360 degrees. If I were to give you a random irregular polygon and ask you for the size of this angle right here, that would be impossible to determine. Based on that, it's irregular. So we cannot make any prediction about one angle. All we know is that all of them together are going to add up to this fact of 360. So trying to determine the size of just one particular angle of an irregular polygon cannot be done. But if that polygon were to be regular, things change. And in that situation, by definition, all of these exterior angles are congruent. So if we don't know how much they are, but we know how many sides there are, we can figure out predictions of this. So our example, right off the SOL test, says here's a given figure, and it's an octagon, and it is regular. And that's very important that we know that all angle measures are congruent, interior and all exteriors. So what's the measure of just this one DCQ, this one angle? DCQ happens to be right here. So how can we determine the angle measure of just one exterior angle, knowing that it's an octagon and all of them are congruent? Well, we take the grand total of all the exterior angles, and we can divide by how many we have, and that'll determine the measure of just one exterior angle. And that gives us this answer right here, 45 degrees. So that brings us to our final idea that we can find the angle measures of anything. That is, given the name of the polygon and that it's regular, we can determine the sum of all of the exterior angles. It's a constant. We can determine one exterior angle. And knowing that they make linear pairs, we're going to determine one interior angle, which means we know all of the interior angles put together. So here's a procedure that will determine all of these angle measures. For this example, let's say it's a 15-gon. Given a 15-gon, determine all the following. Step 1, I would like you to draw just an unfinished polygon, because a 15-sided polygon would take too long. So just draw a few edges of a polygon and draw their exterior angles, and let's just pretend it's 15. The second step is the sum of the exterior angles is a constant, so we just know that answer. All of these will add up to 360. The third step is to find just one of these angles. We're going to take the sum of all of them, 360 degrees, and divide by how many we have. In this example, it would be 15, and that'll give us this one exterior angle, 24 degrees. So the exterior angle is 24 degrees. Find each interior angle. Well, we know for a fact that the exterior and the interior form that linear pair. So if this is 24, the interior is 180. Take away that 24. So that's again going to be 24 plus some number is going to make that 180. And that'll give us 156. Check me with that on a calculator. So what's all of these interior angles added up? If they're all 156s and we have 15 of them, we could do 156 times 15. Or we also had a formula, as I said earlier, 15 take away 2, that's the number of triangles, 13 times 180, will give us that answer. I'll let you grab the calculator and figure that one out. So in review of this procedure, and this is probably the most important thing of the lesson, given the type of polygon we have, determine any of the following of these things. For example, a 20gon. Step 1, we're going to draw a 20gon. No, we're not. We're going to draw an unfinished polygon and extend the edges. Then we're going to find the sum of the exterior angles. Well, that's easy enough. It's 360. We don't have to do anything. The sum of the exterior angles is always the same no matter how many sides. But to find each exterior angle, we're going to take that 360 and we're going to divide it by how many we have. So 20 angles, 360 and divided by 20 gives us 18 degrees. So if each exterior angle is 18 degrees, how much is each interior angle? Well, that's a linear pair. So 18 and 162 give us that linear pair of 180. So if each interior angle is 162, we can either take the 162 and multiply it back by the 20, or we can do 20 minus 2, 18 times 180. And again, you can grab a calculator and find that out on your own. Here's yet one more SOL example, that is in 2004, number 30, stated what's the measure of the interior angle ABC of this polygon shown. So with the procedure I showed you, our first step would be, well, how many sides do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we actually have a decagon. Step 1, well, the exterior angle is going to add up to, well, it's always going to be 360. So if I know all the exterior angles make 360, how much is just one exterior angle? 360 divided by 10 gives us 36 degrees for that exterior angle. So how much is one interior angle? Linear pair with 36 is going to have to be 144. And that gives us the answer 144. One last variation of this question can be, given the size of the angle, like perhaps the interior angle is 150 degrees. How many sides is the polygon? It's kind of the same thing, just a little bit backwards. So let's work this problem a little bit backwards. If the interior angle is 150, then the exterior angle would be the linear pair. This would be 30. So now the question is, how many 30s are there in this picture? How many exterior angles of 30 degrees each would add up to that grand total? So 30 plus 30 plus 30 to make 360, or again 360 divided by that particular number 30 would tell us that there have to be 12 angles. So this thing is a dodecagon. This has been podcast 3-4 Polygons Part 2. Thank you very much.